Hi guys, I'm going to be explaining project 2. This is going to be for aerospace experiments for OSBE. Let's go ahead and close this. So I'm going to open up the SolidWorks file. So I already have it opened up. So I'm going to be doing the right hemisphere, right, because the circle is on the right side. I've already gone and sketched it. It's very simple. So accounting for the 7.5% blockage ratio, the height of the cylinder or of the hemisphere is 0.6 inches, which is already calculated here. It's very simple. It's a line. It's just one line and then a 3-point circle. I just selected here, here, and here as points, and then I just gone ahead and rewrote that. So exit sketch, and then this is what I get for that. And the wind tunnel, this is from project 1, so I kind of just imported that and then sketched over it. And yeah, so we're gonna go ahead and open up ANSYS Fluent and run our CFD. So we're gonna import our geometry. We're gonna browse that. So hemisphere right here. We're gonna open this up and check out the geometry, make sure it's all good. Takes a while. It's gonna process it and then it'll open up, or actually it was fast this time. So we're gonna hit generate. It's gonna generate our wind tunnel along with our hemisphere. As you can see, it's perfect. So this is what we have so far. So we're gonna close this up. And now we're gonna go ahead and mesh that. So we're gonna edit. The mesh is what takes a little longer to open up. Okay, cool. So give it a second. Okay, cool. So this is our wind tunnel. Now we're going to go ahead and create our mesh. So insert method. We're going to select that as a geometry apply. We're going to select triangles. We're going to hit generate. Great. And now we're going to also create, so right inside here, we're going to mesh this area in here. So in order to do so, we're going to hit right click on mesh, insert sizing. We're going to select edges. So as so 2 edges. Number of divisions, we're going to set that's 100. Hit generate. And change our element size, generate. And this is what we have so far. So this is our entire wind tunnel meshed along with the hemisphere. And we used 100 number of divisions for that. So now we're going to name our walls. And then after that, we're going to go ahead and import that into our setup. So we're going to select that, edges, create name selection, wind tunnel walls. And that. So now that that's done, we're going to go ahead and exit out of that. We're going to update our mesh. Takes a second. Okay, great. So now we're going to hit setup. We're going to select double precision. Let's give it a second. So here we have our mesh. Now we're going to go ahead and set up. So viscous, we're going to change the equation to a scalar. Almara's equation. That's all good there. Materials, we're gonna make sure air 1.225 kilograms per meter cubed, perfect. Inlet. So I already had calculated it before, and our 2.3 meters per second gets us really close to 12. Reference values, we're going to change this from inlets, surface body. We're going to create our drag and coefficient of drag reports. So we're going to hit force report, drag. Let's do drag coefficient. Drag force. Okay, perfect. So we're going to close that. We're going to select hybrid. Oh, I was supposed to actually hit 25 here. Let's initialize that. And then run calculation, we're going to change the number of iterations to 300. And then let's calculate that. So that's our drag force. This is our drag coefficient. And it converges, as you can see. Perfect. So as you can see, this is our drag. And from this, we can calculate our coefficient of drag. Also, let me, so we can get the exact number. Console. So our drag force should be 1.2939 newtons. And from this, we can calculate that using the drag coefficient equation, which is drag force over density times velocity squared times area over 2. So we plug this number in for our force and our density, which is 1.225, our area, which is 0.6 inches in meters times 1 meter, and then divided by 2, we should get a coefficient of drag that's very similar for the that's comparable to NASA's hemisphere. So now that's done, we've gone. Let's go ahead and change this out. So okay. Okay, cool. So we're gonna get the static pressure, velocity, and streamline pattern. So in order to do so, the plots, XY plots. Let's do static pressure. That's already selected. We're gonna select all of that. Actually, no, we're not gonna select that. We're gonna create a new surface line. That's one. So that's our static pressure. As you can see, it decreases a bit, and then it runs into the plate, and then it starts to increase again as it goes past the hemisphere. Now we're gonna go ahead and create our velocity. Plot. So as you can see, the velocity increases. It increases as it goes through the contraction chamber, and then it hits the wall, and then it stops. So the velocity goes to 0, and then it starts to increase again as it enters the diffuser or it starts to increase after the plate, and then it starts to decrease thereafter as it enters the diffuser. And that's because of Bernoulli's principle. Okay, so now I also want to create this is an extra part, but I think it's really useful in understanding how the wake region is formed. So let's call this velocity. Let's display that. Let's change this to harpoon. 0.5. So as you can see, this is our wind tunnel, and this is the hemisphere, the right hemisphere. As you can see, the velocity comes in here. This is the patterns, and you can see the wake region right here as it forms. So all of this increases the drag, and it's a decently wide wake region. And you can also see the separation right here for the hemisphere. So I thought this is really useful to know and to visualize it. So now that that's done, we've gone ahead and got our static pressure, our velocity, and now we have to get our streamline patterns. We've already gotten our drag force coefficient and drag force. So in order to get the streamline patterns, we're going to quit this. Let's change, set that. Okay, so we're going to hit results. Okay, so this is the wind tunnel. It's at symmetry 1. So streamline, let's just streamline. I just didn't do the 1. Okay. Okay, that's probably why I just changed the name, messed it up. So this is a streamline for the hemisphere. You can see it goes over the plate or over the hemisphere, and you can see our pattern. Let me actually play around with this. I've never actually done that. Vertex. So equally spaced is the best, in my opinion. So yeah, those are the streamlines for the hemisphere. So this was project 2. I hope this is useful in some way. And yeah.